Okay, in this lesson we're going to be learning about or reviewing using our proportion skills to solve some ratio problems. So I want to go back and explain to you and really examine what we mean by proportion skills and why it works. Okay, so basically a proportion states that two ratios are equal. So we set up these two ratios equal to each other. And basically what we're going to do is we're going to use the fact that cross products of equivalent ratios are equal to solve. So that's kind of the crux of what we're doing here. What I want to do is take a look at the same problem three different ways and explain the connection between the three methods. Okay, so we're going to be solving this problem here where we have 2/3 is equal to some number over 12. We are trying to find the missing component here of an equivalent ratio problem. And this is something we've done before. We look at this and we can say, wow, there's a direct relationship. I know exactly what I did to get from 3 to 12. We had to multiply by 4. And we know that in writing an equivalent ratio, whatever I multiply one of my components by my denominator, I need to multiply the numerator by that same component, that same number. So if I multiplied 3 times 4 to get to 12, 2 times 4 would give us 8. And so this would be an example of a direct relationship here. All of these are going to be direct relationship, but we can see the direct relationship because we're multiplying by a whole number here. Something I want you to take note of is take a look at my cross products when I multiply diagonally here. Now I know this is getting kind of cluttered, but when I'm saying my cross products, I want you to take a look at the outcome when I say 3 times 8 is equal to 24. 12 times 2, this cross product going back this way, 12 times 2 is equal to 24. If I have written equivalent ratios here, my cross products should be equal to each other. And I can use that as a check to see if two ratios are equivalent to each other. I can just check the cross products to see if they're equal to each other. That's a good way to check and know that your two ratios are actually equivalent. Okay, so I'm going to use that fact to develop a second method here. And the second method is what we're getting at when we talk about proportion skills. I have the same problem here all over again. But for whatever reason, I'm having a terribly blonde moment, and I just cannot remember how the heck did I get from 3 to 12. What do I multiply 3 by to get to 12? I have another method. I can look at the cross product where I do have a diagonal of numbers. I can multiply those together. 2 times 12 is equal to 24, and then I can divide by the remaining component that doesn't have a diagonal here. It doesn't have a diagonal partner. So 2 times 12 is 24. 24 divided by 3 is equal to 8. And that is what we call our proportion skills. And what we're doing is we are cross-multiplying and dividing. That's what we mean by proportion skills. Okay, this is the method that we're really going to focus on today and setting up all of our application problems, because I think that's the one that everybody's going to connect with or recall or have the most comfort with. The other thing is not always is it going to be a direct relationship where you recognize that you're multiplying or dividing by a whole number to get from one unit to the other. This would be pretty straightforward. You can do this all with your calculator. Just go to your calculator and plug in 2 times 12 divide by 3 equals, or enter, whatever, and there you've got your answer. So once you set up your proportion problem, you can do your cross multiply divide on your calculator, and voila, you've got your answer. Okay, the other thing that I want to do, okay, this is breaking this into 3 different components here. This was looking at a direct relationship. This was using cross multiply and divide. I want to look at the same problem, but yet a third method. If any of you are familiar or have had algebra before, you will connect that with algebra. You very often, rather than having a blank box or whatever, you use a variable, a letter, to represent your unknown. But we can set up an algebraic equation using the fact that we know if we have equivalent ratios, our cross products should be equal to each other. So I can set up an equation with my cross products. 3 times m should be equal to 2 times 12. So I can set that up and actually now start solving using algebra skills, where you are working your way down a series of steps. 2 times 12 is 24, but here I have to recognize that this is 3 times some unknown number is equal to 24. And with algebra, your goal is to try to isolate that variable. You have to kind of think this through and figure out what's the connection. This is 3 times. This is multiplication. How do we undo multiplication? You have to think about inverse operations. So we undo multiplication with division. So I divide this side to get that variable by itself. Your goal is to isolate that variable. But if I divide the left side by 3, I have to divide the other side by 3 to maintain the balance. So this reduces and I end up with m is equal to 8. So that's just another way to solve it. I know that many students, didn't really like algebra or they didn't ever have it. So I'm not going to do a whole lot with that. I just wanted to present that we could solve many of our problems going forward using algebra. And I'll try to pull that in every now and then. Okay, so here we've got some problems that are, for whatever reason, we set up our equation and this is the equivalent ratio that is in place. So I want you to think through your cross products using this method up here. Wherever I have a diagonal of numbers, those are the numbers that I can multiply and then divide by the lone guy that is left over to find out our variable. So in my calculator, I would say 4 times 9 divide by 12 to get an outcome of 3 here. And so you could just go and do that in your calculator right out of the gate. You don't have to do anything more than that or set up and create an equation or anything. Using proportion skills, you can just plug it in like that. Okay, so this one, here I have a diagonal of numbers, so I can multiply by that and divide by the guy that's left over. So 15 times 50 divide by 10, and I believe that 750 divided by 10 would mean that our outcome would be my outcome is 75. Okay, and this one, here's my diagonal, so I'd multiply there and divide by this. I don't know if that helps you or not. Okay, so 7 times 4 divide by 5 would be 28 over 5, which means that goes in there. 5 and 3/5 could reduce to 5.6. A couple things that I was doing here. Here in this first one, I plugged everything just exactly the way I would enter it in my calculator. I used X here to represent multiplication. Going forward, I don't really like to do that a whole lot because X can also represent an unknown variable. So here I communicated multiplication with the parentheses. Nothing new for some of us there. And here I use the parentheses to communicate multiplication, and I use this slash here over 5 to communicate division. And then I set this up as a fraction problem that I converted to a mixed number and then converted that to a decimal. So again, you're just kind of plugging in all different kinds of skills. All 3 of these, are excellent ways to do this. And in all honesty, you're probably not even going to write this stuff down on your paper. You're just going to go right to your calculator, plug it in, and your calculator's probably going to give you the decimal outcome. I just want to give you those different approaches. Something else I want to point out is take a look at each of these outcomes here. Now, here we found that X was equal to 3. Here we found that P was equal to 75, so I'm putting my solutions in here so you can see a pattern. Okay, so going back, and I know it's kind of cluttered, but looking at 3 over 4 is equivalent to 9 over 12. Look at the pattern, the movement with my numerator. 3 increased to 9. My denominator increased to 12. Here, my numerator increased to 50. My denominator increased to 75. So notice in both of those cases, both the numerator and the denominator both increased. In this one, my numerator decreased from 5 to 4. And here, my denominator also decreased from 7 to 5.6. This is the hallmark of what we call a direct proportion. That's where that term direct kind of comes into play. Is that, notice, either both variables or both unknowns, both components of your problem, either both increased or both components decreased. That's just something I want you to take note of, because when we go on our lessons here in this unit, we're going to find a different pattern evolves in our next lesson. Okay, so now we want to go forward using these skills and applying them to some of our word problems. because this is the whole crux of an applied math class, is being able to apply some of your math. So in this case, this first one, we've got 4 cases of paper, weigh 22 pounds. And we want to know how many pounds 52 cases will weigh. So one thing that I want you to, I think it's helpful if students can put their information in a word problem. What we're doing is we're looking at comparing the weight to the number of cases. So in this first part, we've got 4 cases of paper. So I've got 4 cases of paper that weigh 22 pounds. That is our word ratio, and that's going to have to be equivalent to how many pounds for 52 cases. So our question is where does the 52 go? The word ratio kind of helps you to recognize that, well, the number of cases goes here. So in your calculator, you would go ahead and cross multiply and divide. So you'd be punching in 22 times 52, divide by 4, and you should end up with 286 pounds of paper. That's why we need those skid loaders or whatever to load those heavy cases of paper. Okay, the next one, the proportion concept can be used, different problems that involve similar figures. So we have to kind of know what we're talking about when we say similar figures. Similar figures means that you have the same shape but different sizes. Either one is much larger than the other, the other one is smaller than the other. So we need to kind of keep that in mind. We're going to take a look at a situation where we've got a tree that is 40 feet tall, casts a shadow 70 feet long. So I'm going to draw my tree here. This is supposed to be a tree, and it is casting a shadow 70 feet long. I think a picture sometimes is very helpful. Okay, so this is 40 feet tall, 70 feet long, and it's casting this shadow. What I want you to recognize is that you've got a right triangle in here. Wow, my drawing is not very good here. And we've got this man standing over here, and he is 6 feet tall, and we want to find out his shadow. So we've got a right triangle there as well. So this is the unknown that we are solving for. So basically I want you to recognize that we could set up a word ratio here where we are comparing the height of one feature compared to the shadow of the other. So I'm kind of setting up a word ratio as well as a shell here that we just have to plug in our information. So I'm going to go with my first figure here. The height of the first figure is 40 feet. Its shadow is 70 feet long. And my second figure is the man. He is 6 feet tall, and we want to figure out his shadow. So again, with your calculator, you would, cross multiply and divide. You should be able to plug that in. Again, what you would be plugging into your calculator would be 70 times 6. Notice I'm using parentheses to communicate multiplication. And then I would divide by 40. And I should come up with 10.5 feet. And that kind of makes sense. Okay, now I want you to recognize, and this is part of where sometimes students get really confused or frustrated, is there's other ways to set up a ratio of the same problem and really come up with the same answer. So let's take a look. I could look at the, I could compare the information about the tree to the man. And so this is a little bit different organization here. And I could be looking at the ratio between their heights compared to their shadows. So rather than looking at and labeling this is information about the tree compared to the man, I'm now looking at the tree being a vertical relationship and the man being a horizontal relationship and a horizontal relationship here. So I'm just organizing this a little bit different. So the height of my tree was 40. The shadow of the tree was 70. The height of my man is 6, and I'm trying to find the shadow. So I would cross multiply and divide. And if I look at what I'm plugging in here in my calculator, again I'm saying 6 times 70 divided by 40, which is really similar to 70 times 6 divided by 40. Should get the same answer of 10.5. So I just wanted to point out that you might set up your ratio a little bit differently than your neighbor, and you'll still come up with the correct answer as long as you've organized and plugged things in correctly. Okay, so moving on to another problem here. We've got a wheelchair ramp that must meet the guideline of 1 inch of rise for every 14 inches of run. So we are going to use a word ratio of rise over run. Okay, and we can draw a picture of this, but it's kind of hard to draw it to scale. And that's one thing, you kind of want to draw it to scale. But I know that I have 14 inches of run for only 1 inch of rise there. So this is going to make a really sliver looking thing here, but I've got 14 inches here and 1 inch here. And I want to know what will be the horizontal distance if the ramp is to have a rise of 16 inches. So this is going to make a really long thing here, and this is obviously can't be to scale, but I have to have a rise of 16 inches, and I want to know what is this total distance here. So setting this up, the rise that I'm given is 1 inch of rise for 14 inches of run. And I want to know what will be the horizontal distance of the ramp if there's needed to have 16 inches of rise. So rise goes in the numerator, so I need to put that 16 up here, which means I'm going to be cross multiplying and dividing. So I'll be taking 14 times 16 divide by 1, and I should come out with 224 inches. And students will look at that and say, dang it, I messed up somehow. That's a big number for this problem. 14 and 16 are the numbers that I have in here. 224 inches, for real? I want you to think about that's in terms of inches. This is going to be a really long distance. If I wanted to, I could go to my calculator and say 224 divide by 12, and I'm dividing by 12 because there's 12 inches in a foot. And so I know that when I divide that by 12, I'm going to get 18.5 feet is what my calculator is going to tell me. And so I recognize that, yeah, that's going to be, 18 feet, half of a foot is 6 inches, so 18 feet and 6 inches if I want to put it out, in that form. So all of these would be correct, depending upon how you want your information. But we found this to be 224, and that kind of makes sense that, for a wheelchair ramp to be something that a person who is in a wheelchair can actually execute, can roll up. It can't be too steep. That's why when you go to, public events or public facilities where they have a wheelchair ramp, that the wheelchair ramp is just a very gentle glide going up or down. So it's something that someone in a wheelchair can actually execute. Okay, so